Hello students, this is lecture 7 from unit 1 OEC552-SoftComputing subject. In this lecture we are going to see the fuzzy set operation and what is called a classical set relation, what is the difference from the classical set relation to the fuzzy set relation, and some operation we can perform over the fuzzy set relation. So this is a problem we are going to see for the fuzzy set. This one is a fuzzy set which have the membership value of 0.2 for train, 0.5 for bike, 0.3 for boat, 0.8 for plane and 0.1 for house. And we have another fuzzy set train, 1 for train, 0.2 for bike, 0.4 for boat, 0.5 for plane and 0.2 for house. So we are going to find out all this operation. First we will start with the plane union plane train. So union always prefer the maximum value from this membership. So comparing this 0.2 with the 1, the maximum value will be 1, 0.5, 2, 0.5, 0.3, 4, 0.4, 8, 5, maximum is 0.8, 1, 0.2, 0.2 is the maximum value. Second function we have to calculate intersection. Intersection always prefer the minimum value from this two membership. So minimum value is 0.2, 0.2, 0.3, 0.5 and 0.1. Come to the third question. Calculate the complement of the plane. Take the membership value and calculate the 1 minus. So 0.8, 0.5, 0.7, 0.2 and 0.9 will be the result for the plane complement. Now we come to the D. Take the D. This is train complement. So 1 minus 1, 0, 1 minus 0.2, 0.8, 0.6, 0.5 and 0.8. Next E, plane set difference of a train. That means that we are going to calculate the plane intersection the train complement. Already train complement is in this slide. So we going to take the intersection of this one with this one. Choose the minimum value. So 0.2, 0, 0. 0.5, 0.3, 0.5 and 0.1. Next operation, calculate the plane union train over the complement. So consider this maximum value 1. 1 minus 1 the value will be 0. Consider 0.5. 1 minus 0.5 the value will be 0.5. Consider the maximum value 0.4. 1 minus 0.4, 0.6, consider the maximum value 0.8, 1 minus 0.8, the value will be 0.2, consider the maximum value 0.2, 1 minus 0.2, the value will be 0.8. Come to the next part. Take the plane intersection, the train. Plane intersection train will be the minimum value from this two and go for a complement it. So 0.2, 1 minus 0.2, 0.8. 0.2, 1 minus 0.2, 0.8, 0.3, so 1 minus 0.3, 0.7, 1 minus 0.5, the value will be 0.5, 1 minus 0.9, 0.1, the value will be 0.9. So next one, go for a plane union plane complement. Plane value is 0.2, the complement value will be 0.8, so the value will be 0.8 because we prefer the maximum value. Here also 0.5. Here the maximum value is 0.7, 0.8 and 0.9. Last question. Take the intersection of these two. We have to prefer the minimum value from the plane and the plane complement. Here the plane is 0.2, plane complement is 0.8, minimum value will be 0.2, 0.5, 0.3, 0.2 and 0.1. Next question. Take the train union train complement. So train is here, train complement is 1 minus 1, 0. So take the maximum value 1, 0.8, 0.6, 0.5 and 0.8. Take the intersection, we have to prefer the minimum value. So here it will be 0, 0.2, 0.4, 0.5 and 0.2. So what is a classical set theory? It always contains sharp boundaries. Fuzzy set theory held unsharp boundaries. Classical set is having exact boundaries and it don't deal with the uncertainty. But we have here ambiguous boundaries can be handled in the fuzzy set. It is used in the fuzzy controllers, but classical set theories are used in a digital system design. So what is the relation? So we take two different fuzzy set and map the different fuzzy set that we call as a relation. We have a connective also. So the classical binary relation represents the presence or absence of the connection or interaction between the two sets of elements. Fuzzy set relations are generalization of the crisp binary relations, allows the degree of membership between the element set. Consider that crisp Cartesian product. Take the crisp Cartesian product. I have elements in the A. A belongs to the capital A set, B belongs to the capital B set. Then A cross B give the ordered set of pairs of A comma B. You can represent the Cartesian product in this format. Instead of a 2 set, you can combine n set. Constrain that A1 has to belong to the capital A1 set, A2 belongs to the capital A2 set, An belongs to the capital N set. This is a binary relation. Binary relation gives the ordered pair of x comma y. The constraint x has to belong to the A and y has to belong to the B. This way we can represent the crisp binary set, one by using coordination diagram. For the x equal to 2, what is the y value? X equal to 3, what will be the y value? That way you can correlate the x set with the y set, or you can go for a biparty graph. Collect the elements of A in one set, collect the elements of a B in another set, write the elements here, and write A1 is related to the B1 in the B set, A2 is related to the B2 in the B set, A3 is also related to the B2 in the B set, A4 is related to the B3 in the B set. Or we can write the graph structure by using arcs. You can represent the relationship. Here 1, 2, 3, 4 are 4 set. 1 is related to itself. 1 is correlated to the third set. 2 is related to itself. 2 is correlated to the first set. 1 is related to the 2 set as well as 3 set. 4 is related only to the 1. We can write the matrix format also. So A1 is related to the B1 in the B set. A2 is related to the B2 in the 1 set by 1. A3 related to the B2 be represented by the 1. So either the set is having relationship or does not have the relationship. If it is having relationship, we represent by using the 1 or the value of 0. We don't have any partial relationship in the crisp set, crisp relation. Operations are, you can go for union, intersection, complement of the two relation, containment relationship. We can go for identity. Properties for the crisp relations, commutativity, associativity, distribution law, involution, idempotent, De Morgan, law of excluded middle. Composition of the crisp relation, we can go for max min and max product. If you use the max min, you have to prefer the maximum value from this two membership function. Inside we have to apply the min operation. Same way for a max product, take the two membership value, go for a multiplication. From that group, we have to prefer the maximum value. Now we consider the fuzzy relation. Fuzzy relation is the mapping from the Cartesian space x to y in the interval of 0 to 1. In the crisp set, we have a relationship either 1 or 0. Now we have the degree of relationship from the first fuzzy set to the second fuzzy set. A cross B always belong to the interval 0 to 1, including 0 and 1. We can represent the crisp relation. Here this is a crisp relation. For the same crisp relation, you can relate the fuzzy relation. A to B is related. A to C is related with the 0.8 degree of membership. B to A is related with the 1.0 degree of membership. C to B is related with 0.9 degree of membership. C to D is related with 1.0 degree of membership. This is the matrix represent the relationship from the A set to the another A fuzzy set. What is the degree of membership value represented here? It starts from the 0 to the maximum value of 1. Operations for the fuzzy set, we can apply the union, choosing the maximum value, apply the minimum intersection, choose the minimum value, go for a complement, or it satisfies the containment. We can go for inverse also, or transport matrix of the R. x cross y is equivalent to the y cross x, then the R is equivalent to the R inverse. Projection, you can project some portion of the R from the y by using this projection operator. Some elements we can take and that we can project to the through the relationship, projection relationship. So property for the fuzzy relationship: commutative, associative, distributive, involution, idempotent and De Morgan law. Now we come to the Cartesian product of the fuzzy relation. We take the fuzzy set called the R. It is a subset of M and S is the fuzzy subset of the N. Then R cross S always be the subset for the N cross M, such that we take the minimum value from the two membership function R and S. We will solve one problem under this Cartesian product. Take this set, fuzzy set having the membership value of A by 1, B by 0.8, C by 0.2, 1 by 1, 2 by 0.5, 3 by 0.9. Then R cross S can be identified for this problem. Okay, how to identify the R cross S? Take the R relationship and S relation, R fuzzy set and S fuzzy set. Choose the minimum value. Compare this A with the values of the second fuzzy set. A value is 1. 1 I am going to compare with this 1. So minimum value for this one value will be 1. 1 I am going to compare with the 0.5. The value will be 0.5. 1 I am going to compare with the 0.9. The value will be 0.9. So we got the first row of the set. Take the second value B, 0.8 with the one which value is 0.8. So we got the 4 elements for the T. We compute the remaining values. Compare this B with the second component of the S, 0.8, 0.5, the value will be 0.5. 0.8 with the 0.9, the minimum value will be 0.8. Take the C, compare with this 1. 0.2, 1, the value will be 0.2. 0.2 with 0.5, the value will be 0.2 again. 0.2 I am going to compare with the 0.9, the value will be 0.2 again. So we got the T is a Cartesian product of R cross S. The answer will be like this. Okay. Now we come to the second operation, what is called the max-min composition. This is also another composition applied over the fuzzy relation. So we have a two fuzzy relation R and S on the set of A, B, C. So R is a subset of A cross B and S is a subset of B cross C. We can correlate the R and S through that max-min or max product. So what is the operation? Inner side we have to prefer the minimum value from the R comma S. After that we have to prefer the maximum value from this two group. We will go for one example. Consider the set x1, x2, y1, y2, z1, z2. It has some number of membership value. After applying the x cross y and y cross z, we got this two relationship. Here x1, x2, y1, y2, y1, y2, z1, z2, z3. We want to correlate these two based on the max-min relationship. First we take this portion, is it x1. I am going to compare with this set, this one with this one. So what will happen? I have to choose the minimum value from these two. 0.7, 0.9, the value will be 0.7. 0.5, 0.1, the value will be 0.1. So maximum value from the 0.7, 0.1, the value will be 0.7. So consider the second one. Take the same row, consider the second column. 0.6, 0.7, the value will be 0.6. 0.5, 0.7, the value will be 0.5. So minimum value 0.6, 0.5, maximum is 0.6. Take the value row again, compare with the third column. The value will be 0.7, 0.5, 0.5. Here also 0.5, the value will be 0.5. So we got the first row. Do it for the second row also. Take the same samples. 0.8, 0.9, the value will be 0.8. 0.4 comma 0.1, the value will be. Comparing 0.8 with 0.9, the value will be 0.8. 0.4 with 0.1, the value will be 0.1. Take the maximum value from 0.8 comma 0.1, the value will be 0.8. So take again 0.8 comma 0.4 for a second column of the S relation. We will compare the 0.8 with 0.6. 0.6 is minimum. 0.4 comma 0.7. 0.4 will be minimum. Comparing 0.6 with 0.4, the value will be 0.6. Take the value again for the third column. 0.8 with 0.5, the value will be 0.5. 0.4 with 0.5, the value will be 0.4. Comparing 0.5 with 0.4, the value will be 0.5. So the resultant matrix will be like this. So this is the max min composition for R and S relation. Same way we can use this R and S composition for max product also. Now we proceed with the max product. So there are two operations we can perform over the fuzzy relation. One is the max min, another one is a max product. That Cartesian product you can use it for two fuzzy set or fuzzy set to the fuzzy relations. So two fuzzy relations R, S are defined on the set fuzzy set A, B, C. R is the Cartesian product of A cross B. S is the Cartesian product of B cross C. Now we are going to compose the R and S. Indirectly it composes the fuzzy set A, B, C into one relation. The solid circle indicate we are dealing with the max product. If it is a hollow circle, we are dealing with the max min. Now we check how to calculate the membership value. This is a max product. Take the membership value, multiply them. From the multiplication, the list of multiplication, we have to prefer the maximum value. That is the relationship, define the X to the Z. So choose the maximum value. From the membership value of X to Y, multiplication of Y to Z. So we will go for one example now. Consider this example again. X2 equal to X1 comma X2, Y equal Y1 comma Y2, Z equal Z1, Z2, Z3. We got two fuzzy relation R and S. So R contains X1 and X2, Y1 and Y2. Here the S contains Y1, Y2, Z1, Z2 and Z3. Now we proceed the same thing for a max product. First we take this X1, X2 to this Y1, Y2 of Z1. How to do this one? We got to multiply this. 0.7 into 0.9, the value will be 0.63. 0.5 into 0.1, the value will be 0.05. Maximum value from these two is 0.63. Take the same row again for a second column. Multiply this 0.7 with 0.6. The value will be 0.42. 0.5 into 0.7, the value will be 0.35. So the maximum value from this two is 0.42. Take the row again. Take the column of the S, third column of the S. 0.7 into 0.5, the value will be 0.35. 0.5 into 0.5, the value will be 0.25. So comparing these two value, we will get the 0.35. Now we got the first row of the max product composition. 0.63, 0.42, 0.25. Now we take the second row of the R relation. Multiply this 0.8 with 0.9, the value will be 72. 0.4 with 0.1, the value will be 0.04. Maximum value is 0.72. Take the 0.8 into 0.6 for the second row and 0.4 into 0.7, 0.48, comma 0.28. The value will be 0.48. Take the second row again with the third column. 0.8 into 0.5, the value will be 0.40. 0.4 into 0.5, the value will be 0.20. The maximum is 0.40. Now we got the relation max product of R and S. So this problem you can try it as an exercise. So you have to take this 2 for a Cartesian product, then you get the R relation. Take this B and C, get the Cartesian product and get the S relation. For the R and S, you can go for a max min and max product. The tilde symbol indicate we are dealing with a fuzzy set and fuzzy relations. Thank you, students.